Welcome back to the deep dive. Today we're jumping into a really fascinating piece from nature physics. Yeah, this one's pretty cool. It's about trying to create these super exotic states of matter. Exactly. These things called quantum spin liquids, or QSLs. And they're using some cutting-edge tools like Rydberg atom arrays. Very precise stuff. So, our mission today is to unpack how they're doing this, the methods involved, and while there's a bit of a surprising twist in their findings, it makes you rethink how we look for these states. Okay, so let's get into it. Quantum spin liquids, QSLs. What are we actually talking about here? Well, imagine a magnet, right? The little magnetic bits, the spins, they usually line up. Fridges, magnets, that kind of thing. With QSLs though, these spins don't order, even at like absolute zero temperature. They stay messy, but it's a very specific kind of correlated messiness. No magnetic order, but they have these long-range quantum correlations. So things are connected even far apart. It's quantum entanglement acting over long distances. And they also have these unique particle-like things. Anyonic excitations. Anyons, right. Not quite your standard particles. And this is important for quantum computing. Hugely important. The dream is topological quantum computing. These QSLs, because of their structure, they're inherently robust. Robust how? Like they don't get easily disturbed. Precisely. Robust to local perturbations, a stray field, a little vibration. That makes them amazing candidates for topologically protected quantum memory. Your quantum data would be way safer. Okay, so super promising, but they're hard to find, hard to detect. That's the big challenge. You need clear signatures. People often think about models like the toric code, which links to something called a resonating valence bond state, or RVB. That's sort of the ideal picture. So how are these researchers making or simulating something like this? Rydberg atoms. They arrange these atoms, specifically Rydberg atoms, on what's called a Kagome lattice. Kagome lattice. That's the one with the triangles and hexagons. Looks a bit like a woven basket. That's the one. It has special geometric properties, and they use a neat trick called the Rydberg blockade. Okay, what's that? If you excite one atom into a high-energy Rydberg state, it actually prevents nearby atoms from being excited simultaneously. Like a little zone of influence. Like a quantum keep-out sign for its neighbors. Sort of, yeah. And they don't just, find the state. They have to make it dynamically, meaning it evolves over time. They use a specific dynamical preparation protocol. They carefully ramp up certain control knobs, things like the Rabi frequency and detuning. Think of it as gently guiding the atoms into the desired state. But there's a catch. It has to be timed just right. It needs to be faster than what we call adiabatic evolution. Otherwise, you just end up in a boring simple state. But it also needs to be slow enough so you don't accidentally kick the system into higher unwanted energy states. It's a real balancing act. And simulating all that quantum action is, well, computationally pretty heavy. Incredibly heavy. Standard methods often hit a wall pretty quickly with systems of this size and complexity. So, how did these researchers tackle that simulation problem? This is where a really powerful technique comes in. Time-dependent variational Monte Carlo, or TVMC. TVMC. Okay, what makes that special? Well, first, it's scalable. They simulated systems up to 288 atoms. That's, significantly larger than what quantum hardware can typically handle for this kind of problem. 288 atoms? So it lets them look beyond current experimental limits. Exactly. It can also handle the long-range interactions that are crucial in these Rydberg systems. And maybe most importantly, it gives you direct access to the time-dependent wave function. The wave function, so the complete quantum description of the state as it evolves. That's right, which means you can calculate things, measure properties with incredible precision directly from the simulation. Okay, now the twist. They simulate this QSL-like state, What did they find? They were looking for a specific signature. The gold standard for proving you really have this kind of topological order is something called topological entanglement entropy, or TE. Explain that a bit more. How does it prove topological order? Scales with the size of the boundary of a region you're looking at. Think like area law. But in topologically ordered states, there's a constant negative correction term, a universal value independent of the size, like a hidden number subtracted off. Exactly. It's symbolized by gamma, and seeing that specific negative value is a direct sign of the deep long-range entanglement that characterizes topological order. For the specific kind they were hoping to see, this Z2 order, the TE value, gamma, should be ln 3, natural log of 2, which is about 0.693. Okay, so did they find it? Well, here's the kicker. The state they simulated did show local properties that looked a lot like that ideal RVB state. Things matched up with what experiments might see locally. Okay, sounds promising, but it lacked the TE signature. The TE value they calculated peaked around 0.479, give or take. It never got close to that expected value. So close, but no cigar. It looked right locally, but the global signature wasn't there, and they checked carefully. It wasn't just because the simulation was too small, finite size effects, or some random spurious perturbations. The lack of the full TE seemed robust. So what's the big takeaway here? What does this mean for the field? It really tells us that just because something looks like a QSL locally, maybe showing some properties you expect, doesn't mean it has the true deep topological order. The dynamically prepared state wasn't quite the ideal RVB state they were shooting for. It lacked that pure Z2 signature. It highlights that local probes aren't always enough. You really need these global measures. So, for you listening, the critical point is this. In these really complex quantum systems, just looking at the surface, the local behavior can be deceiving. You need tools like TE, these global quantities, to be sure you've actually created the exotic state you think you have. And it also shows just how powerful this TVMC simulation technique is becoming. It's likely going to be a leading tool for designing and optimizing experimental protocols going forward, giving us insights experiments can't easily get yet. Which leads to a pretty important question, doesn't it? It does. What does this tell us about that fine line between just being QSL-like versus having genuine topological order? And maybe more broadly, as we build more complex quantum tech, how crucial will refining these global probes be to make sure the fault-tolerant systems we want are actually what we're building? That's the million-dollar question right now. How do we guarantee you've got the real deal? Something to think about. That's all for this deep dive. Thanks for joining us.